Welcome to your tutorial on ray tracing as a means to find image distance and height in concave mirrors. So, to start with, you'll need to construct yourself a little old concave mirror. You have to, if you remember the major parts of your concave mirror, you have a center of curvature, a focal point, a principal axis, and the mirror itself. When you construct your concave mirror, you need to make sure that the center of curvature is actually the radius of your mirror. If it's not, your ray tracing will not work. So you can use a compass or you can sort of freehand it, but you do need to make sure that the center of curvature is actually at or very close to the center of the arc that you're using for your concave mirror. You also need to make sure that your focal point is exactly halfway between the center of curvature and the mirror surface, and that your principal axis is right in the middle of that mirror. Okay? So I'll give you a moment to do that. You may want a straight edge of some sort, some paper, and a compass. Okay. Are you ready? We're going to place our first object in front of our concave mirror. Okay, now that you have your concave mirror constructed, we're going to place an object outside the center of curvature. So, a couple key points to remember. The distance that your object is from the mirror surface is your object distance. Object distance is given by the letter P, and it's always positive because the object always has to be in front of the mirror. An object placed behind the mirror's surface will not cast a reflection. Okay, a few other things to remember. The focal length is the distance between the focal point and the mirrored surface, and that's given by a lowercase letter f. In a concave mirror, the focal length is also always positive because it's in front of the mirrored surface. Any measurements that we get that have a negative sign refer to distances behind the mirrored surface. Those are where we get negative numbers. Okay, let's get started. You're going to like this. It's a pretty easy way to confirm the results of your image height, image distance, and magnification that you've gotten mathematically. Kind of like graphical construction of vectors is used to sometimes confirm the algebraic solution for a vector problem. So, we do a ray trace using 3 rays, all straight lines, all starting from the object. In this case, I've got a little candle. It's sort of traditional, and we're only going to use one point on the candle. We're going to use the very top, and so that represents the top of the image then in the spot where we find our reflection. Okay, the first ray we're going to do is a straight line that goes directly from the top of the object to the mirrored surface, and it has to be perfectly parallel to the principal axis. Now, when that ray strikes the mirror, it's going to reflect back, and the reflection for your first ray will pass through your focal point. If you draw this well, you get a perfect result. If you're a little bit sloppy, you get a slightly sloppy result. We'll see how well I've done. So that's my first ray, and I typically put an arrow somewhere on the ray to remind myself which direction each of those rays is passing. So again, we've taken a ray from the object to the mirror, and it's coming back through the focal point. Okay, on to our next ray. Our second ray, and I'll choose a different color, is also going to start at the object, but this one's going to pass through the focal point before striking the mirror. So we line this up, and I'll put my little arrow on it right there. Now, when this one reflects back, it will reflect back parallel to the principal axis. So here's my reflection line. We'll see how well I can do using this program. Okay, that's interesting. 2 of our reflection lines are now meeting. Now we're going to draw one more ray, and that ray is going to again start from our object, but this one's going to go directly through the center of curvature to the mirrored surface, and then oddly enough, it's going to reflect back on itself. Oops, can't get an arrow there. There we go. It's a bad arrow, but hey, look at that. We have a point where all three rays meet. Guess what? That's where the top of this image would form. And because the point where the image forms is below the principal axis, we know the image is inverted. We could actually, if we had done this really, really well, we could measure the height of the image, and we could actually figure out magnification this way. We're not going to do this, but I'd say this is probably a reduced image. It's probably slightly smaller than the actual object. So we know that it is, what we should be seeing in our mathematical calculations is a positive image distance, because the image is forming in front of the mirror. We should be seeing a negative magnification, because the image is inverted, and a negative magnification means we are seeing an inverted image. And we should probably, if I was a betting person, be seeing a magnification that's less than 1, because it sure looks to me as though this image is smaller than the original object. It is actually that easy. Let's do a couple more examples just to get you comfortable with it. This will allow you to take all of the concave mirror problems that you've been assigned to do mathematically and draw a ray tracing to confirm your results. Okay, we have a slightly different setup here in that we've now placed our object between the center of curvature and the focal point. You'll notice that here the object was outside the center of curvature, and we got a real inverted reduced image. Now we have an object that's between the center of curvature and the focal point, and our ray tracing approach is exactly the same. Our first ray goes from the object to the mirror and reflects back through the focal point. Whoops, I forgot to clear out the words underneath C and F to make room. Okay, we have our first ray. Now, our second ray is going to go from the object through the focal point to the mirror, and then from where it strikes the mirror surface, it's going to reflect back parallel to the principal axis. Can't really tell if my line's perfectly parallel. We'll see soon enough. Now, this is the trickiest one. We have to draw a line from the object through the center of curvature that reflects back along itself. But wait a second, the object is inside the center of curvature. What we're really doing here is creating a line that connects the center of curvature, our point on the object, and the mirror surface. So we will do, it's a little tough here, we'll do, oh, I didn't quite do it right. That line. Okay, and this is where we see how sloppy my work is. What do you notice immediately? Well, my three lines don't meet. What that means is that I've drawn at least one of these badly, possibly more than one. What we see is an area where it looks like they sure want to meet. Two of them meet, but my center of curvature line doesn't quite match up with the other two. If I look more carefully at this, I'd say that my very first ray probably wasn't parallel. Let's try the first ray over again. Okay, here we go. I'm going to do better this time. Parallel to the center of curvature. I think that's closer to parallel. Then back, whoops, back through the focal point. Okay, well, still not perfect, but it sure does get us a lot closer. When three of your lines don't meet, you want to start to look for one of them that isn't really parallel, and if you're using a drawing app like this, sometimes you can't get the lines perfectly parallel, but you're going to get close. If you're doing it with pencil and paper, you should be able to achieve perfectly parallel lines. Now, let's look at a few things about this image. Okay, even though we don't have an exact spot for the image, we're pretty close. And a few things we know right off the top. Well, the image distance, Q, should be positive. Why? Because the image is formed on the front side of the mirror. So this is a real image. We could actually project this onto paper. What else do you notice? Again, even though our ray tracing isn't perfect, it's good enough to tell us a few things. We would expect to see a negative M because this image is clearly inverted. The point where the three rays meet is below the principal axis. And again, even though it's not a perfect meeting place, we can tell, even with this sort of bad estimate, that the magnification is definitely going to be greater than 1 because the image is significantly larger than the actual object. Okay, these are all things that we can tell from a ray tracing diagram. Let's do one more example, and then you're on your own to practice. Okay, what do you notice immediately? Well, we've got our object now inside the focal length of the mirror. Despite that fact, the ray tracing diagram is done exactly the same way. So, let's take our first ray, and we're going to draw a line from the object to the mirror, perfectly parallel, or as perfect as we can get it, to the principal axis. Now, we're going to run our reflection line back through the focal point. There's our reflection line. Okay, so far so good. Now, we want a second line. I'll pick my second color. And we're going to draw a line from the object through the focal point. Again, this is inside the focal point, but we can still draw a line that connects the mirror and the focal point, and that's our inbound ray. This is where those become really important. And then our reflection is parallel to the principal axis. Hold on a second. I got a serious problem here. At this point in our other two examples, we'd had at least 2 lines meet up. What in the heck is going on? Well, let's draw our third line and see if that fixes things. Okay, third line connects the object through the center of curvature and reflects back along itself. Okay, mirror, center of curvature, object. Okay, this didn't get any better. What's wrong with this picture? Well, this is by far the trickiest because in fact, these 3 lines don't converge in front of the mirror. So what you have to do is run your lines, continue them, back behind the mirror. Oh, look at that. So again, sloppy drawing on my part, but when you continue those reflection lines, not the inbound lines, but the reflection lines, you find an area where the 3 lines do meet. It's just behind the mirror. And again, my lines on this one are especially sloppy, so my meetup is not perfect. With pencil and paper, you should be able to get a perfect meeting point. Now, if we were to sketch out the object that we're seeing, even with this sort of bad, sloppy work, we immediately see a few things. The distance behind the mirror, or our image distance, Q, would be negative. Why? Because the image appears behind the mirror. That means this is a virtual image. This image cannot be projected onto a piece of paper. We also see something else really quickly. Our magnification, M, would be positive for the first time because this image is going to be upright. The other thing we see is that even with a sloppy drawing, we know that the magnification is going to be greater than 1. Why? Because the image is clearly larger than the object that's being reflected. So it's got a magnification greater than 1. You've enlarged the image. Okay, let's walk through the 3 steps real quickly, and then I'll turn you loose. Okay, you have a concave mirror with your principal axis, your center of curvature, and your focal point marked. No matter where your object is placed in front of that mirror, we always start off the exact same way. Number 1, First draw a ray from the object to the mirror, parallel to the principal axis. Reflect that ray, that's your inbound ray. That ray gets reflected back through the focal point. Okay, second ray. Second ray goes from the object through the focal point to the mirror. There's my inbound ray. And then it reflects back parallel to the principal axis. At this point, you should start to get a sense of where all three lines are going to converge if you're doing really well. Okay, third line. The third ray will go from the object through the center of curvature to the mirror. And there's my inbound ray. And of course, my outbound ray is the same thing because it reflects back along itself. Hey, that one's not too bad. Where at least two of the lines, and if you're doing really well, three of the lines cross, that's where your image is going to appear. An image that appears in front of the mirror has a positive value for the image distance, and it is a real image. It can be projected on a piece of paper. An image that appears behind the mirror has a negative value for image distance, and it cannot be projected. It's a virtual image. An image that appears below the principal axis will have a negative magnification because it will be inverted. An image that appears above the principal axis will have a positive magnification because it will be upright. An image that is larger than the object that you were reflecting is going to have a magnification greater than 1, while an image that is smaller than the object will have a magnification less than 1. Okay, with these tools for ray tracing, you really can't go wrong, and it's a great way to back up the mathematical work you've done finding your image distance, image height, and magnification. Good luck!